Hi, everyone. I'm David Greenberg. Welcome to episode 28 of the Machine Learning Seminar at Hereon. We have an interesting paper today. Marcel Nonnenmacher is going to present. And this paper trains neural networks to do preconditioners for linear solvers as they'd be used inside of a fluid dynamical model. And a common criticism of machine learning methods in earth sciences, fluid dynamics, other physical sciences is that, while they might be maybe more flexible, trainable, and in some cases faster, they're less accurate than physical laws in cases where we have good models. And what's interesting about this paper is they find a way to use machine learning in such a way that it simply helps the physical model do its job, and it can't introduce any new errors. So with that, I'm going to turn it over to Marcel.
Hey, everyone. So yeah, as David explained, today we're going to look into this paper, which was put on the archive last October from Ackmann et al. So jumping right into the abstract, so as David explained, so today we're going to talk about increasing the performance of some linear solvers, which come up in semi-implicit time update steps. We're going to look at an example from the shallow water equations today. As David pointed out, the application is very nice in that it circumvents some potential robustness issues with machine learning, in that especially with deep learning, you're never quite guaranteed that what you get out is going to be good under all circumstances. But in this case, you're learning a preconditioner that you will still solve for a linear system, which you will still solve with whatever method you used before. So you still have some control over the accuracy, which is a nice change. They do write that their preconditioner method is highly flexible regarding complexity and machine learning design choices, which is a nice way of putting that what they're looking at here is a concept of doing things. It's not an out-of-the-box method that will work everywhere. You will have to do a lot of design choices yourself, depending on the model that you're using and the exact context of what you want out of it. So as I said, it's going to be about the shallow water equations, shallow water model here. So they have this figure in the paper where they include some parts of the solutions. So the equations are 1, 2, and 3 here. The first is a conservation equation. The second and third equation is momentum related. On the right-hand side down here are 4 and 5. Are pretty long equations. You can see in here, you see H0, which is the topography, which plays a role in this. What we will be mostly interested is equation 1, because the way equations 2 and 3 are solved is they're being solved explicitly. So what's going to happen is we're going to isolate the temporal derivatives for these fields on one side of the equation, put everything else on the other side, discretize in time and space, and then we're going to solve with an explicit method, say either everything in forward Euler in the brutal case, or some half steps or something. And this is going to be purely forward computed from the current states at time n of the field phi, the fluid thickness, and the momenta and the other terms from the old time level. Now, more interesting is how the fluid thickness itself is handled with the solver. They kind of glance over the details on my paper. So this is going to be the implicit part. It's going to be a linear problem by the end of the day, for which we have to solve for the fluid thickness of the next time step. So it's going to have this shape where L is going to be a linear operator. Think of it as a matrix once we have actually discretized everything. And R is going to be, well, if everything's vectorized, it's going to be either a vector, discretized. It's either going to be a vector if you vectorize phi, or it's going to be a map, like the same shape of phi. If phi is this latitude longitude grid, then R is going to have the same shape. And then, yeah, we want to solve this where this is 0. And in this case, L is going to have some particular shape. But they have this equation is actually in the paper. It's actually has some meaning because this is a well-studied form of these linear operators, for which there's some theory. Just in case you wondered why they would write this down. L represents the discretized implicit terms, and R incorporates the explicit part of the time integration. So this might already contain whatever intermediate solutions we computed for the momenta. So both L and R might be rather complicated functions of phi and the momenta at time point n. But for the particular problem, these are going to be fixed. We're trying to solve this fixed system of linear equations for this phi at n+1. And how do you do this? Well, you use a numerical solver. In goes whatever describes your system of linear equations, and out comes your solution. If this were a small problem, you would just call your numerical solver. I don't know. I like to code in Python. So I just call numpy.solve r, L, I think is the syntax, and then I take out the result and move on. In this case, however, we're talking about really high-dimensional systems where solving these is actually a challenge. And the way it's usually handled is you do this iteratively. So you start with first guess for this quantity that you want, and then over several iterations, you minimize the error until you reach some threshold that tells you you're close enough to ground truth. And then you take what comes out. So this is the type of solvers that we're dealing with. In particular, this one is going to be called the generalized conjugated residual method, or conjugate, I think. In the paper, you're going to find in the appendix this flowchart, which essentially just summarizes what's going on. I'm not sure if you can read this on your screens, but it essentially says you need an initial guess for this quantity, phi at n+1, and then we iteratively improve that until we're done, which is given by some exit condition, usually some norm of the error or some norm of the change from one iteration being smaller than some epsilon. Now, in the paper, I realized this kind of algorithm is a bit just stated that they're going to use this. So we're going to do a small detour over some other paper that luckily has the very same notation. So there's not going to be much transfer needed from our side. But that kind of explains this very nicely. And I want to go over this very quickly, so I will rather liberally interpret what is in there. If you want to have a look, I will have the exact citation for this paper at the back at the end of the presentation. So they deal with the exact same problem here, nicely with the same notation. And the idea of how to actually solve this iteratively is they write down a differential equation, as you do in the geosciences. And this is a linear differential equation, an inhomogeneous one, unless R turns out to be 0. And for this type of linear dynamical system, as the time goes to infinity, this thing will go to the solution of S. So this will be 0 on the right-hand side in the end. Then what you can do is you can discretize this. You can go, you can introduce some delta t from which goes from time n to n+1. They call this beta here. And then if you bring this to the other side and you divide by beta, you're going to see this is like a forward Euler approximation of these dynamics. And then if you iterate this many times, you're gonna forward the system. And if this is a convergent system which converges to the exact solution, you're gonna get this exact solutions. This is the rough idea of this. Now, if you have this, you might immediately ask yourself, well, how quickly is this gonna converge? Well, that depends on the eigenvalues of this operator, this linear operator L. There's some mild constraints on L that you want for this to converge in the first place, like negative definite, which also Ackmann et al. In their paper say their L has this property. And then the question is like, what are the eigenvalues? Like if they're very, very close to unity, nothing changes much, not much changes in one short time step. So you want to have a large delta t. If they're all very, very small, close to zero, then things develop very fast, and you're gonna converge very quickly, anyways. The problem is when there is spread in the eigenvalues of L. This is something, well, L you compute. This is something you don't really have under control. So what you can do is you can start with preconditioning. So if you write down this system where P is another linear operator in this case, and you do the same discretization of the dynamics, you're going to find that the update step now looks like this. And here we first encounter this residual R, which is short for, well, how far away from solving are you actually? And if you look at the shape of this, you're going to see that the inverse of this preconditioning matrix on discretized space is just a matrix, just gets multiplied with the linear operator that we have from the system we're trying to solve. And then the question is no longer what are the eigenvalues of just this linear operator, but product of these two matrices. And this is a way of controlling the spread, the clustering of the eigenvalues. And now, how do you choose this P? Well, if the preconditioner were the linear system, then, well, the result would be the identity. The identity has all eigenvalues equal to 1, so you have very nice clustering, and you're going to converge very quickly. In fact, if you set beta to 1, I think this will converge in a single step. The problem is, well, you need to invert P, which in this case you would have the linear operator. So you kind of already need the solution for your problem, your system of linear equations, because if you have L inverse, you can get the solution pretty quickly. In the other extreme, well, you don't use preconditioning, you set P to the identity, which implicitly you've already done here in this form, and then you get no acceleration. So a good preconditioner is going to be somewhere in between. And as they nicely wrote in this paper from 2000, I think, there is great flexibility in designing preconditioners. It's a bit of an art, and it's also very problem dependent. Like the structure of L, sparsity of L is all going to go into what makes a good preconditioner. So with this, we're going to go back to the main paper. Quick summary. So we've seen systems of linear equations can arise from semi-implicit schemes. We've seen this on the shallow water equations. At scale, you would usually solve them with iterative solvers. So we've seen this generalized conjugate residual method in the paper. It's nicely explained in this paper here. You need to do 1 or 2 more steps from here to get the exact algorithm we see in the main paper today. But these steps are described actually in here. And then preconditioning can benefit iterative solvers by clustering the eigenvalues. And one way of achieving this would be you pick a preconditioner whose inverse is the inverse of the linear system. So with this, we go back to the main paper, and especially to the algorithm that is described here. And one thing you will notice if you actually look at it, you always require the inverse of the preconditioner. That's the first thing. And the second thing is you only required it already applied to a vector or a field of residuals. You don't need the preconditioner itself, and you don't even need its inverse. So what you could try from this is, from a machine learning perspective, well, we're going to learn a mapping that takes a residual vector and it directly maps onto this. So we could train a neural network which does this mapping, and then we're not asked to return the preconditioner as some output, which would be a really, really big matrix in some cases, but the neural network itself is going to implement preconditioning. And then, well, what is going to be our training target? What are we training the network with? What is it supposed to do? Well, we already said a good preconditioner has this property. It's close to the original linear system, so that its inverse is close. Well, if you then apply this to the actual residual, you're going to find that if you do the equation for the residual, you're going to find that what it's supposed to predict is the difference between phi nu, I think this is pronounced. So phi nu is the current estimate of, in our case, the fluid thickness within the current iteration of the iterative solver. And this here, phi n plus 1, is the solution that we want. So it's supposed to take in the current residual, and it's supposed to predict the difference from the current fluid field to the desired solution. And I'm not entirely sure if I do the math. I think they have a minus sign missing here, but maybe I'm wrong. The point is, this is what you want to predict. And this is a hard task. Like if you just have the current estimate of the residual, you generally don't have the information to actually predict this, the solution, right? You don't have it yet. But what you can do is, so this is what this would look like. You would have a neural network which just takes the current residual and then outputs this difference. And again, if the current residual is a field, say on a latitude-longitude grid, a 2D array, then the output will have the same structure. And this is how you would compute the residual, just plug in the current estimate of the fluid thickness. Now, what you can do for training is, well, if you have a simulation, a numerical simulation, then you have a whole sequence of fluid thicknesses, and you can compute the right-hand side here, which is the difference of subsequent states along, the trajectory which you simulated. And then you can plug in the 0th iteration, which I think it's not really spelled out in the paper. It's going to look like this. And then you can have a training signal for the neural network, which is going to try to have the output of the neural network mimic this difference via some mean squared error. So this is all pretty standard now. But the important thing is, well, you might want to train this for every individual state along the iterative solve. But what you can do quite easily is you can train something very close to it, which is just on the actual states of the solutions along time. There is one quick fix, because these two things are not going to always be the same, because as you iterate the solver, the residuals is going to have more to do with the solution than with what you started out with. And they do have a little fix for this by always normalizing everything, because as you increase the count of the iteration, the residuals would shrink and shrink and shrink. So there's some disappearance of this over rounds, which you don't really see during training because you're always going to have the 0th iteration. So they're already trying to somehow account for this difference between what they actually train on and what they want to train on. But it's not going to be the exact same thing. So keep this in mind. And yeah, so this is what this will look like in terms of architectures. They try out different neural networks. Each neural network takes a certain region of the input space around the pixel. And from this, it tries to predict the difference, this difference across the time step of fluid thickness at this pixel. And they try different neural networks with a different number of layers. So 5 layers with 200 hidden units, 1 layer with 5 hidden units, and then L0, N0 is 0 hidden layers with 0 hidden units. So this is just a linear mapping. And then they try out 2 different sizes of relevant input regions, 5 by 5 and 3 by 3. And then you will see from the structure of this graph, they actually train different preconditioners for different latitudes of the grid. So this is a latitude-longitude grid, and the closer you get to the poles, the more these grids converge towards these grid points, converge towards a singular point. So there's distortion. So it makes sense to train different algorithms for different latitudes. And one thing that you might appreciate here is that the different neural networks here in different versions of red, they all behave pretty much the same in terms of their quality. So this is a performance metric. What really makes a difference is the size of the stencil, 5 by 5 versus 3 by 3. And so this is the part in the manuscript that I didn't fully understand, to be honest. So the authors seem really surprised, positively surprised that the linear 5 by 5, so this red line, model 5 by 5 linear, that this performs really well. If you think of it, what it's supposed to do, well, a linear model can be written in this form, where you have some matrix A, whose rows are given by the output of the neural network. If you have 5 by 5, then in each row of this matrix A, you're going to have 25 non-zero elements. If you use a 3 by 3 stencil, you're going to have 9 non-zero elements. But overall, this matrix A is supposed to mimic the inverse linear operator of the true system. So the whole thing is supposed to be a linear operator. The more surprising thing that you can learn this very well with a purely linear network is that you can learn it really well with a 5 by 5 stencil, at least to me. Because you actually don't really know how sparse the inverse of the linear operator is going to be. Yes, so these are the main results. You can do this with a well, quote-unquote linear neural network, which you may also just call a linear operator, to do the to learn the preconditioner, one latitude at a time.
So can I jump in with a question?
Yeah, sure.
Something I'm struggling with a little bit is, so I think I get what's happening when you use a linear preconditioner, in that, if your update is a solution to your system of linear equations, if you multiply both sides of this linear equation by a matrix P inverse, it's still, what was the solution before is still a solution after you do that transformation, right? But what's actually going on when you use a nonlinear neural network? What is all this talk of eigenvalues and linear solutions when now you're performing nonlinear operations on each iteration?
That's a good one. So as I said, and I think a lot of people can appreciate, the idea of the preconditioning is a linear operator. So we have this here. It's a linear operator if you have a linear preconditioning matrix. If you follow this idea, that what you're doing is, you're multiplying, as you said, both the left and the right-hand side of the linear system with some matrix. Now, as I tried to explain, if you have some matrix L with some sparsity structure, then its inverse might not be as sparse. So the target might not just be non-zero at 25 different points, or 25 different locations, as you would have with a 5 by 5 stencil, right? So it might be that they hope that they have a limited range 5 by 5 stencil, which is nonlinear, to make up for that.
Right, but then, I mean, are there any convergence guarantees anymore, or is it just, okay, we train something to reduce the residual in this linear system, we hope it works. If it doesn't work, we go back to our old-fashioned linear iteration, but there's no convergence guarantees the way there are based on eigenvalues of the linear update, right?
I mean, it still holds. One thing that still holds is if you have a system of linear equations and you have a solution, right? So this is equal to this, then any nonlinear function applied to either side, well, it's going to have identity if the arguments are the same, right?
I mean, if it is a solution, then you're applying it to 0 on both sides, and then it's still, a solution of this new nonlinear system. But if it's not a perfect solution, there's no argument, like based on eigenvalues or something, that the error should decrease over iterations anymore, right?
I'm not entirely sure. You have a good point here. You might be, depending on if you have a very nonlinear one, you might actually be introducing multiple possible solutions or something.
For example, yeah. Okay. Okay.
That's a good point. One thing that might really help preventing very funky things from happening is just this restriction to 5 by 5. But yeah, that's something to actually think about. You're right. I haven't really thought about this. So here's the 5 by 5 stencil of the linear operator for the preconditioner that they actually learn. And it's just nice to see that this does make sense. So these are the mean absolute values, if I understand it correctly, that they get. And you see that the stencil element for the center, which is the pixel, if you want, that you're trying to predict the difference between the fluid thicknesses. This one has the largest value, and then you have along the two axes, you have also heightened importance of the input that you're feeding into the network. So this doesn't tell you that it's working particularly well. This just tells you that it's intuitively makes sense what it's trying to learn. What's way more interesting is how does this actually play out. So this is now looking at what we actually want out from these solvers. From these preconditioners is we want to have that our iterative solvers for finding the solution to our system of linear equation, which is the fluid field, the next time step, that these converge quicker. And the first way to look at how how you define quicker convergence is just looking at the number of iterations. So if we just look at without preconditioner, the type of systems of equations that comes out of the shallow water equations, as they looked at them, the iterative solver usually from its initialization converges up to a quality threshold, an error threshold that we're willing to accept within about a dozen iterations. And if you use the preconditioner learned by machine learning with these linear preconditioners, you can cut that down to around 7 iterations. So not quite half, but close to. Then there's the baseline, which is a non-machine learning one, which we're going to talk about in a moment, but you can still get this a bit quicker, actually. So if we just focus on the machine learning preconditioner versus no preconditioner, we can say like it works. It does what it's supposed to do. It converges now much quicker, and it doesn't cost us much more, because what we have to do is we have to apply the preconditioner, which, well, if we don't use any, we don't have to. But the preconditioner that they wrote down is pretty fast. It's a linear one, so the preconditioner itself is very easy to evaluate. It's a linear function with a 5 by 5 stencil. And it's what we call embarrassingly parallel, meaning for every individual pixel of the field, every individual location, you can do this independently. In particular, the way they wrote this up, which is a fully connected neural network, which is applied to small patches, 5 by 5 patches. So you can just have this, the whole field of the whole field, every single 5 by 5 region for every individual pixel, every single location here, you can feed it in parallel, and then you can write this all into one big array, collect the results. And so this is really quick. And
can I ask another silly question, maybe? The residuals here, that's L infinity, meaning the biggest absolute error across the entire grid. Now, in figure 1 that you showed, the heights of the fluid are in the range of 5 to 6,000 in some units, I guess meters. These residuals are 10 to the 9th. How did, no matter what the initialization is, how are we seeing such big errors?
That's a good one. I don't know what the initial values are.
When you said in the paper they initialized to 0, but yeah, somehow they're off by 10 billion. What is it, the distance to the moon or something?
That's a good one. I don't know. Is it maybe They do have code online for this, I should say. One could check this. Maybe they do have a square in there somewhere.
Could be. Okay, cool.
But yeah, you're right. The y-axes are at the moment a bit weird, but maybe it does make sense if you look at the code. Okay, so overall it does work. In terms of pure number of solver iterations, it doesn't work as good as a baseline. But one thing they do write in is that the baseline algorithm that they compare to, which is also described in the appendix, but for interest of time, I'm not going to go over the details. This thing actually takes some time itself. So I think they write that it's about 4 times more expensive to evaluate than their preconditioner. And they say that both preconditioners result in the same computational savings of about 30% overall. So even though in number of iterations that the solver still needs, this one, the ML solution is kind of inferior. The preconditioners do not seem to give that much of a gain as we see over here, just because it's so quick to evaluate the machine learning preconditioners, you come out comparable. Okay. Now, we still have that the number of solver iterations is not reduced as much. So one question you can ask at this point is, what is still limiting the ML preconditioners in this study? And of course, you can go through the usual, did they have enough training data and so on and so forth? Did they use the right optimizers? Could they have squeezed out more? But more on the principled side. But as we already talked about, they use these 5x5 stencils for their preconditioner versus the true inverse linear operator might have way more relevant entries per location than just 25. So they didn't really write that whether or not they tried 7x7 and 9x9 and would have still gotten an improvement. At least if they did, then I overlooked it, and I'm sorry. So maybe this is the limitation, which is a choice of the model complexity. Then we already mentioned there's more of a nuance regarding training, in that they always predicted from the 0th iteration of the solver the distance. Why this is relevant is as the iteration count new increases during an actual iterative solve, this distance would shrink. So here your method is used to predict 1 delta t ahead, like the typical distances you get along whatever time step they have, and we're talking about a semi-implicit scheme. So you use this because you want to have larger time steps, and you would have a purely explicit scheme, and it's only trained on those. And during evaluation, you're gonna run this on residuals which are really small, such there isn't much to predict anymore. And it is okay somewhat for their purely linear preconditioners, because as you increase the iteration count, the residual is going to shrink, and so the distance is going to shrink because everything's linear. The residual is 10 times smaller than what comes out of the network is going to be 10 times smaller. But this might be something to consider. Like, you could probably not just save the actual states of the shallow water equations, numerical solver that they do have, but also the intermediate one, and try to reach the train. And then lastly, maybe the biggest point, but the one where I'm really speculating the most is the motivation of their loss came from trying to roughly set the preconditioner or the inverse of the preconditioner to be close to the inverse of the actual system of equation via this relationship. But from the original motivation of what a preconditioner does, actually what we care about is directly the clustering of the eigenvalues of this combined matrix. So my question would be, is there ways of targeting this more directly? I have to say I'm not aware of anything right now. I know that there is stuff like the nuclear norm, which is targeting the sum of the singular values, which would be the sum of the eigenvalues squared, but not something that actually targets the variance. But maybe this is something one could look in as an alternative for training.
I think that's a really insightful comment. I would just add in that it's not only the full set of eigenvalues that you want to reduce, but also the eigenvalues that correspond to the eigenvectors, which actually look like the residuals you'll obtain.
Yes. Yes. Yeah, so that just doubles down that this first clause for motivating this, it was well motivated, but it's kind of more on an intuitive level than something that you really want to actually have in the end. But yeah, so these are some speculations towards the end. With this, I would conclude. So here's the promised citation for the second paper. I will try to update like the description of the YouTube model of the YouTube video in order to incorporate this. And those of you who are interested, yeah, you can have a look at this as well. Yeah, and that would be it from my side. Are there any questions? Anything unclear?
I have a question.
Sure.
And maybe you can go back to the slide where you show the different models like L0 and whatever these curves.
In terms of performance, right?
Yes, with this one, right. So we're trying to get a preconditioner which saves us the most time, right? And shouldn't in this plot on the y-axis, the relative MAE decrease, what I didn't get, shouldn't be better? Because we're trying to get as much decrease out of a conditioner as possible?
I would have to check up what MAE actually means. It's probably maximum something. Let me quickly switch to the
I think what they mean is the absolute
right?
value of the error after divided by before, which is it's not a good way of naming that.
So this would be the error of the targets of the neural network. Like what you're actually training on is, sorry for having to search this now, but I'm in the actual paper. You want to predict this, and you check what you actually predict. And this would be on this axis. This is not yet the time saving. This is related to this, probably. They don't actually show this, I think. But this isn't the axis with the time saving. You don't want to be high. This is how well you're
that was related. Okay. Yeah, okay. Thanks.
No problem.
I would have a general question for everyone attending, and maybe especially anyone more familiar with these different types of solvers in atmospheric and ocean models is, what are the views in earth science and geophysics right now about implicit versus explicit solvers? I see arguments for each. I've talked to people that are very surprised that anyone would ever consider one or the other, that you definitely want to use implicit or explicit methods. Can anyone say anything about kind of the general views of people in the field on these two different approaches?
I mean, all I can say, I worked on the shallow water equations for the German Beidirk quite some time, and my conclusion was I could not do without an implicit solver for cases where you have extremely shallow water and where you have extremely nonlinear effects due to the friction in this very shallow layer. Explicit schemes just didn't work. So I think in some cases you just don't have an alternative. So these implicit schemes are more stable. I think one could say that they're of course also more expensive in general, although you can use longer time steps in general. But I think in some cases there's no alternative.
Thanks a lot, Johannes. That's actually very illuminating. I mean, a pattern I picked up on is that people seem to use implicit or semi-implicit solvers more for regional models and more for ocean and other kind of waterway models, whereas atmospheric models and global models tend to be explicit. Is that something you've noticed as well, or is that is there reasons for that?
I'm really not a specialist regarding the atmospheric models. But yeah, as I said, my experience was with the strong nonlinearities in these small scale or regional coastal ocean models. That was really a problem with the explicit formulation. And I think all the models that I know somehow have, which somehow try to model coastal ocean, they somehow have an implicit component in them, even if it's not very visible. But I think usually they have some implicit component. And about the atmospheric models, I just don't know.
Oh, thanks a lot.
Maybe one more general question. First of all, I find this whole approach extremely interesting, and I think the idea is just really nice to combine this, let's say, classical implicit scheme approach with the neural network and just with the goal to speed things up. That's a really nice approach, I think. My question was, we are also coming across these big non-linear systems in the framework of data assimilation. And my question was, are you aware of some studies where they try to apply this to symmetric operators? Because that's mostly what we have to deal with in the context of these minimization problems.
You mean this kind of study specific for symmetric? I would not be aware, because this is like the first study in this direction.
So it's really the first study of applying neural networks for these preconditioners at all.
That I am aware of. I mean, it's from October last year. It's like half a year old.
Yeah, no, that's really super interesting. Yeah, because we are trying in 3D VAR, for example, we are applying conjugate gradient methods. But again, we have to deal with symmetric operators, but also really big, so we cannot store any matrices and so on. Of course, there you also have the standard approach of using preconditioners, but usually we are just using the inverse of the prior covariance matrix and things like that. And so if there was an alternative, because even, I mean, there's some more classical preconditioners like, what is the name? I think incomplete Koleski decompositioners, something like that, that you could also think about. But for the dimensions that we are dealing with, that's not even an option. So I don't know, for this application, I was wondering if classical preconditioners like incomplete Koleski decomposition, if they did consider that as an alternative, or did they do comparison?
Well, here in this study, they do this comparison against this one classical conditioner, this implicit Richardson. But just regarding the size, yeah, as I mentioned, in principle, this should scale really well because it's parallel. The way they compute the preconditioner matrix is extremely parallel. The one thing you do need to sorry, I'm looking for this. The one thing you will need to compute is well, the residual, for which you will need one row times one column of the matrix and the vector, at most, for being able to locally compute this vector and then feed it into the network. So if you have gigantic matrices and so on and so forth, you could probably write their stuff in such a way that you never go beyond linear scaling of the size of the system.
But maybe that could be an interesting, as I said, in our case, L also has a banded structure, like in this case also, but it's symmetric. So maybe, so you would probably assume that it's somehow getting easier, but I don't know. But I think that could be an interesting application of this method. For 3D VAR, I think.
I would recommend you, I mean, if you're interested in this, I would recommend you really reading this this paper. They have this big part, they have an own section on this, on self-adjointness, like in which case it becomes easier. And if I understand it correctly, and I'm really not an expert here, self-adjointness pretty much boils down to symmetry of L. And they go into some details and what you then may additionally assume. And then one could think of how this actually helps with what they're doing here, because they explicitly do not assume that it's self-adjoint. So this might become easier.
Yeah, maybe that's, I will try to read it, but that's really super interesting. Yeah. Thanks a lot.
Johannes, are you talking about the shallow water equations or some other model?
No, I'm talking about the, are you aware of, or are you familiar with the 3D var scheme?
Yeah.
So, I mean, there you basically, it's a linear least square problem with a really, really big matrix that you cannot even store. And the way we are, I mean, we have applied this in the context of SST assimilation into a 3D circulation model. But it's not really in the model, but it's really, I mean, it's a second separate analysis step. So you are taking the first guess from the model, you're taking your observations, and then you have to somehow model your a priori knowledge about the correlation properties of your model errors. Put that into this big matrix, and then you have to solve this linear problem. You get an analysis, and then you feed this back into your model and restart your model. But still, you have to deal with this really big linear system where you basically can only store state variables, and there's no way that you can store matrices or anything like that. You just have operators and state vectors, basically. And yeah, and in conjugate gradient methods, I mean, the convergence rates are definitely an issue. I mean, it's really slow compared to other methods where you can actually store matrices.
Sounds like a really interesting
that's actually
problem.
used, sorry?
It sounds like a very interesting problem.
Yeah, and that's actually, I mean, 3D var is used at weather centers like UK Met Office also. And I mean, they have even bigger state vectors, so they put everything into the state vector, their whole model. And I could imagine that could be an interesting application, this method.
I should also say, I'm very sorry if I rose any suggestion here that this was tied to this generalized conjugate residual method, but this kind of approach that they're following here with machine learning preconditioners should be rather independent of which method you're actually using to solve the system of linear equation. So if you go with something like, I don't know, red, black, gauss, idle, or other high dimensional solvers for high dimensional systems, it should also still work.
Yeah, actually, that was another question I had, because I was actually not familiar with this paper you showed about the variational approach. And I wondered, is this somehow related to successive over-relaxation, these SOR methods? It somehow looked a little bit familiar. It's also
I'm not aware at this moment. I can't say, I'm sorry.
Yeah, but yeah, so you can, of course, you can, that pops up in various applications, in various problems, minimization problems, and nonlinear zero crossing problems, and so on. These preconditioners, it's the big challenge, let's say.
I would have one more question, but I want to let anyone else go first who has any thoughts or questions on the paper. All right, well, let me just quickly pose this question. So what I was really surprised by is that when they start off with their neural networks and their linear models for the preconditioner, they start off by feeding in as input all the residuals in a 5x5 region, but also the coefficient fields. In fact, what you've got on your screen right now, all the terms that get multiplied by the different partials of capital Phi, the second partials, the mixed second partials, the first partials. So you have all these additional coefficients which can be used to compute the preconditioner. But then they say, actually, this doesn't help and they don't get used, at least at the poles. If you look at supplementary, then they do get used a little bit at, say, 60 degrees north of the equator. But why would it not help to use this? And is this maybe why we, right, that's figure S2, right? Here you can see these other coefficients being used. But why doesn't it help? And why, could this perhaps explain why they're seeing much better performance at the near the equator than at the poles in terms of the error reduction? Maybe because, you know, most of the poles are kind of a rare case, and that you know, it just learns one set of one basically matrix P inverse that works kind of best there.
I mean, regarding the poles, you also have this other effect that the points just get physically closer, so they're going to be more correlated. So at the extreme pole, you're going to end up with essentially one independent data point per time step. Because at the equator, they're much more independent. You might have as many effective data points as you have grid points in the extreme case.
Interesting.
Yeah, regarding this, I must admit I didn't quite follow the idea in the first place to give them these fields individually, because what by the end of the day matters for the system of equations is just L, right? Just what comes out when you sum them up. Individually don't play as much role. If they help predicting L inverse locally, okay. But if, like here, they're just added up in this linear fashion, if I understand this correctly, this isn't just linear in phi, this should actually also be linear in these coefficients, then you could just learn one linear mapping that does, you know, work with all of them.
But the coefficients vary in space, and they vary depending on the you know, they depend on the nonlinear explicit part, right?
Okay.
They're going to be different at every time step and every location in space. So you'd think that taking them into account would help you build a better preconditioner, but it seems not to be the case.
I must have then admit that I didn't get the complexity of these things. I haven't actually seen them and how they're computed.
Okay, so that maybe remains a bit of a mystery. Finally, last question from me. What's up in figure 1? Are these grid artifacts we're seeing in the images?
Figure 1, is that the example solution?
Yeah.
Okay, should be below the abstract. You mean especially towards later?
Well, you can see it in all three of these 5 values. You can see something like a regularly repeating grid. It looks like sometimes you see this when you apply convolutional networks to images.
Oh, you mean especially like around here, huh?
Yeah. Some kind of computational mode, but you see it in all three of them, really.
Yep. I don't know. Might be that they're using a very large step size or something.
Yeah, they said they use 240 seconds, which is within the Courant limit. Though, of course, that you don't have to do that for implicit methods. Like maybe for the explicit part. Yeah. Okay. Cool. That's it for me. Anybody else have a question? All right. Well, thanks a lot, Marcel. This was a great presentation. I feel like we might see some more developments on this line of research from the same group before or during the peer review process as it moves from archive to a journal. So maybe we'll see some interesting surprises. So we'll kind of keep an eye out. Thanks everyone for joining.